Now, the following part of the chapter is about the test of independence. What are we testing in there? We want to test if two variables are independent from each other. Okay, so we have two variables. In this case, we have the variable 1 and the variable 2. Okay, this is variable 1, this is variable 2. We have over here the observed values that follow in this. In each one of the variables has different categories. Whatever. Category 1, 2, 3, and 4. And for the variable 2, we have also different categories. We have the observed values. We have the totals over here. Okay, and we have the totals over here. Okay, and the total, of course, is right here. And is exactly the same. This is the observed value. We have to calculate the expected values. Okay? And at the end, we are going to have the test is equal to the double summation. Why? Because I'm going to write it down with black. The double summation, and this is my test value, of what? Exactly the same. F minus expected squared divided by expected. Of why double summation? Because we have to go through the m from 1 to m and from 1 to n, where m is the number of columns and n is the number of rows. And at the end, we are going to test again a high square, and this is again an upper tail test. This is alpha. With how many degrees of freedom? Okay, we need to calculate the degrees of freedom. How many degrees of freedom? M minus 1 times, or n minus 1 times n minus 1, where n is the number of categories in variable 1, and m is the number of categories in variable 2. That's it. So simple, so easy. That's it. And again, we're going to use our high square with these degrees of freedom. N minus 1, the number of categories, and n is the number of categories in variable 1, and m is the number of categories in the second variable. And we want to know if the two variables are independent. Basically, probably the situation where we employ these kind of things is, are there difference in the way that men and women behave? Are they behave differently? Are they the preferences independent from the gender? And so on. Or I don't know, promotion in a company. Is the promotion dependent on the gender? Are there some type of discrimination, gender discrimination, and so on. Okay, but then basically, this is how you do this. Now, you have the observed. What is the expected? The expected, if this element is independent from the two variables, it's this number times these numbers divided by the total number. And this is the expected number. Why? Because we have the total number of elements in the category 1 for variable 1. We have the total number of elements in the category 1 for variable 2. And we multiply this number times these numbers divided by this one, and it goes in this cell. Okay, let's do an example, and probably it will be easier to understand this. Okay, it's complicated, the math, but it's pretty straightforward. It's not that hard. Okay. Let's do problem number 18 in your book. It says, sample taken in 3 cities. So we have 3 cities: Anchorage, Atlanta, and Minneapolis. So we have 3 cities. So location, 1, 2, 3. What is that? Anchorage, Atlanta, and Minneapolis. Anchorage, Atlanta, and Minneapolis. Okay? And we have the percentage of married couples with both the husband and the wife in the working force. Analyze the following data to see whether both the husband and wife being in the workforce is independent on the location. Use alpha is equal to 0.05. And what is your conclusion? So, what is the null hypothesis? They are independent. What is the alternative hypothesis? They are not independent. So, location against the percentage of couples where the both men and women works. Okay, so we have both or only one. And we have this one. This is what they found. 57, 33, 70, 50, 63, and guys, the book has a one mistake. It should say 27 in order to match with the it says 90, but it's 90 over here. The total elements of data taken from Minneapolis. Okay, so the total data from Minneapolis is 90. From Atlanta is 120, and from Anchorage is 90. Okay, the total number of elements that both the couple both work is 190, and the total elements that only one works is 110 in the 3 cities, with a total of 300. So we have 300 households that they got the data from, and they got this data. So this data over here is what is called the observed. Okay, we need to calculate the expected, and this is the expected number of elements if both variables were independent. Okay? Now, what should be the expected number of elements of Anchorage where both couples work if the location and the status of the couple would be independent from each other? Okay, for this element, it could be 90 times 190, so it's the total of the row of the column times the total of the row divided by 300. For this one, it would be 120 times 190 divided by 300. For this one, it would be 90 times 190 divided by 300. For this one, it would be 90 times 110 divided by 300. For this one, it would be, for this one over here, it would be 120 times 110 divided by 300. And for this cell over here, it would be 90 times 110 divided by 300. So this is the expected number of elements if the number of, they would be independent, the location from the status of the couple. So I already did it, and this is 57, this is 76, 57, 33, this is 44, and this is 33, okay? If they would be independent. Now, first of all, we need to know the I-square with the critical value over here. We know that this alpha is equal to 0.05. They already gave it to us. So, but how many degrees of freedom? This is a I-square. How many degrees of freedom? Okay, how many rows or columns do we have? We have 3 minus 1. How many rows? 2 minus 1. So this is equal to 2 times 1 is equal to 2. 2 degrees of freedom. So we need to know what is that critical value. So go to the I-square with 2 degrees of freedom and 0.05. And this is 5.991. Okay. Now, so how are we going to do the test? Remember, it's a double summation. So for each row and for each one of the columns, we want to do what? The frequency minus the expected square divided by the expected. So this is the frequency. This is the observed. Is 50. So let me do this. 57 minus this 57 squared divided by 57 plus the next one. 17 minus 76 squared divided by 76 plus 63 minus the expected 57 squared divided by 57 plus the next one, the following row, 33 minus this 33 over here squared over 33 plus the following, 50 minus 44 squared divided by 44 plus the last one, 27 minus 33 squared divided by 33, and this is equal to, this is 0, this is 0, and this is some other things, and this is equal to, at the end, 3.014. Now, where is this 3.014? It's over here. So it's in the do not reject zone. So we conclude that we do not reject the null hypothesis. So we conclude that these variables are independent, basically. There is no real dependence between the location and the status of the couple. Okay, so we do not reject. Indeed, we do not accept that they are independent, but we really do not say that the evidence tells you that they are dependent. They are not independent. So, but basically, this is how you do the test of independence between two variables. That's it. I mean, it's probably complicated in the process, but it's pretty straightforward. So we do not reject. Let me put it in here. And we conclude that we do not have enough evidence to say that these variables are dependent from each other. So we may say that these variables are independent. Okay? Basically. That's it.